Well, thank you very much, Andreas, for that introduction. And thank you, everybody, for coming and giving me an opportunity to share with you what I've been working on. So like Andreas said, I've been interested in large-scale machine control using surrogate modeling techniques, specifically Bayesian, from the Bayesian viewpoint. And in this case, we're applying it to multi-objective optimization. So when we think about kind of developing algorithms for controlling or assisting in the control of accelerators, we want those algorithms to have several characteristics. We want to be able to have those algorithms optimized towards multiple objectives at once, which is something that often happens during machine tuning today. We also need those methods to satisfy multiple operational constraints. And we'd like them to be able to quickly find reasonable solutions in order to reduce overall tuning time. And then finally, we'd like them to be able to handle noise and drift while taking into account previous data from past experiments and simulations. So to motivate this, I can provide this example problem that we have. So this is the cesium telluride photoinjector at the Argonne Wakefield Accelerator at Argonne National Lab here in Illinois. And for this photoinjector, ideally, we would like to minimize a bunch of different facets of the beam simultaneously, including the three emittances, 2 transverse and 1 longitudinal, the bunch size in three-dimensional space, and the energy spread. However, reducing some of these objectives stands in contrast to others. For example, if we wish to minimize the longitudinal bunch length of our beam at low energies inside of the photoinjector, this often comes at a cost in terms of transverse and longitudinal emittances due to space charge effects. So as the bunch is compressed longitudinally, the space charge forces cause the beam to become more disorganized, increasing the overall emittance. And so we would like to find a solution with our 6 different tuning parameters that will simultaneously balance each objective against each other in order to find an overall ideal set point. When we do that, normally we simply use an algorithm to propose a point that we will measure in real life, and then we simply measure that point, and then add that to the optimization algorithm. However, current optimization algorithms have relatively poor sample efficiency. In this way, for example, it takes a large number of samples in order to perform the optimization. And when you have to sample a large number of points on an accelerator, this takes an increasingly long amount of time, especially when you have very complicated diagnostics and other factors are involved in the amount of time that it takes to make any one measurement. Our objective in multi-objective optimization is to find what's known as the Pareto front. The Pareto front is a set of points that ideally trade off between objectives. So on the plot here on the left, I show 2 objectives, F1 and F2, which we both wish to minimize. And the Pareto front essentially tracks the dominant points, i.e. the points that are better than all of the other possible measured points, or at least as good, and then better in one objective than any other point. And what this gives us is, it gives us a Pareto front, which says which points give optimal trade-offs between the two objectives. So you'd like to find that Pareto front and then choose a set point where the objectives are Pareto optimal. One way that we can characterize the Pareto front is known as the Pareto hypervolume. The hypervolume essentially is, in the 2D case, is simply just the area between the Pareto front and a reference point shown here on the right in the top right corner, is essentially just a calculation of the total area of that parallelogram given by the points on the Pareto front. In higher dimensions, this turns into a hypervolume. And so we wish to use an algorithm that proposes points that hopefully increase the hypervolume of our Pareto corresponding to our Pareto front. And once the hypervolume converges to a large number, we say at that point, then the current Pareto set is the actual Pareto front. One very classical way, and it's interesting that we say classical now, even though it's been developed, within the past 20 years. NSGA2 is a genetic algorithm that proposes samples or set points based on a biomimicry principle, where we essentially select the best individuals and then have them cross over their individual attributes and then add in a chance for mutation in a generational sense in order to slowly improve the fitness of a population until it reaches a large Pareto hypervolume. Now, this is done generally in a massively parallelized sense, where you have independent computational processors evaluating the fitness of each individual in parallel. And so, for example, we can have 100 individuals, and we improve the population over 175 generations in order to maximize the Pareto front hypervolume in a computational simulation of the photoinjector problem that we had before. However, the major issue with this comes when we want to translate this algorithm to practical use in online optimization.
But I like it short, that's why. It looks good though.
Sorry, can you mute your mic?
Salsa.
I guess I'll just continue. Okay, so in the case of practical implementation of this algorithm for online tuning, since the accelerator cannot be operated in parallel, the fact that we need so many individual evaluations of the individualized fitnesses becomes a major roadblock. So for example, if we are going to do an optimization, in this case for the photoinjector problem, it took 17.5 thousand observations in order to find a roughly ideal Pareto front. And if we want to do these observations in a serialized manner in an accelerator, that takes maybe 5 seconds to make a single observation, our optimization time is going to be over 24 hours long. And this is obviously not practically feasible for any online tuning algorithm. There's been some progress in this respect with improving the efficiency of genetic optimization by combining it with Gaussian process surrogate modeling and neural network surrogate modeling. So an example, I have a couple of examples here from SLAC where people have combined this genetic algorithm with Gaussian processes or neural networks in order to efficiently do pre-sampling on a surrogate model to determine the ideal points where we would actually do our physical sampling. And however, these methods are still not ideal due to the fact that they're relying on a heuristic in terms of sample generation, which, while is a large improvement over the normal genetic optimization, still is not sufficient for online optimization. So we'd like to, the name of the game here is doing this optimization with as few physical observations as possible, because that is what costs us most in terms of time needed to reach an optimum. This is where Bayesian optimization comes in. Bayesian optimization contains three different parts. It contains a Bayesian surrogate model, an acquisition function, and an optimizer that optimizes the acquisition function. And in this case, these three parts come together to generate a test point, which we will observe in our physical machine. So I'll quickly go over the different parts of the Bayesian optimization algorithm here. So the first part is a Gaussian process surrogate model. What this model does is it predicts the function value as well as a corresponding uncertainty of the function for every point in input space, using Bayesian statistics and updating a prior model into a posterior using observed points. So in this case right here, I've shown a one-dimensional example of a function that's being modeled by a Gaussian process. The blue here is a prior distribution. It essentially says that we have little to no information about what f of x looks like. And then we make observations at points in input space represented by the black dots that we use to update the probability distribution of the function value everywhere in input space, depending on a kernel, which we specify beforehand, that simply specifies the pseudo rate of change of the function value as a function of the length scale associated with where we are observing and where we are trying to make our predictions. We then use this surrogate model, so it predicts both a mean function value, which is shown as the red line in the center, and the uncertainty, which is shown by the red shading, to predict, along with an acquisition function, in order to choose ideal points that are likely to be optimized in choosing our next physical sample to measure. In this case, I have shown an example of a simple acquisition function known as upper confidence bound. Upper confidence bound simply takes the mean that the Gaussian process predicts and adds on a scaled uncertainty. And we simply, that's given by the orange line at the top. And we simply choose the point in input space that maximizes this acquisition function to observe in our physical system at the next step. The advantages from this are sizable, specifically because we are allowed to specify a trade-off between exploring our input space or exploiting certain regions of that input space to take advantage of what we imagine of the predicted extrema of our surrogate model. It also inherently in the sampling process improves the model accuracy in the regions of interest, namely where our surrogate model expects to be at a local maxima. Now the question is, how do we adapt this for multi-objective problems? In this case, what we do is we take, for each objectives, we have an independent Gaussian process model. And in this case, our acquisition function is no longer the upper confidence bound of our single objective, is now based on the predicted improvement to the hypervolume over the currently measured Pareto set. And that's shown here on the right, where the blue shaded region denotes the current hypervolume in a 2D objective problem. And the hypervolume improvement is shown in green. And the predicted mean and uncertainty for each of the objectives is shown as the cross and the orange shading respectively. In this case, we use our surrogate model to predict which points in input space will give the largest increase in hypervolume based on the surrogate model prediction. And that allows us to, in this case, we are explicitly calculating out what the increase in hypervolume is, which should significantly reduce the number of measurements needed to increase the overall hypervolume. I plotted a 2D example here on the left with a little animation. So I have two objectives, F1 and F2, which are simply parabolas in the 2D input space. The ground truth of each of those objectives is shown on the top row of the plots on the left. And then in the middle row, I have the Gaussian process surrogate models for each of them. And I'm also plotting my physical observations with red crosses. On the bottom left, I see a plot of the acquisition function in 2D space, which is simply just the average increase in hypervolume as a function of input space based on my surrogate model. And then on the bottom right, I'm plotting each of my observations in the 2D objective space. And what we see is that just making new observations where the maxima of our acquisition function are, we slowly but surely start to observe points that lie on the analytical Pareto front, which is given by the blue line, which also happens to be the line between the centers of each of my ground truth minima. Now, in the case of our accelerator problem, specifically the photoinjector case, we have a large number of objectives. However, this expected average hypervolume improvement calculation is relatively slow in a high dimensional objective space. So you can actually use a simpler method akin to upper confidence bound and just specify a kind of lower confidence bound hypervolume improvement metric for our acquisition function, which is shown on the right. And this allows us to calculate a optimistic view of the hypervolume improvement much faster in high dimensional spaces. And that brings us back to our photoinjector problem. So now I will take this multi-objective Bayesian optimization, or MOBO for short, algorithm, and apply it to an accelerator physics problem, namely this photoinjector optimization one. Now, in order to do this, there's two ways that I can kind of benchmark this problem on benchmark this accelerator problem. The first is to directly run PIC simulations, particle tracking simulations on a large computing cluster such as BBOP at Argonne National Lab. But alternatively, I can use recent progress in neural network surrogate modeling to reduce the computation time for evaluating each input and the resulting outputs by using a surrogate model of the AWA photoinjector that was developed by OWLE and everybody else at SLAC. And so this allows me to rapidly test and improve these novel optimization algorithms. And so this is the result. So on the left here, I've plotted the Pareto front hypervolume as a function of the number of observations. And in blue, we see the MOBO case, which quickly rises and then plateaus around 90. And in this case, all of the objectives are normalized. So this is normalized units right here. And I can compare this to an NSGA2 algorithm, which clearly shows, the MOBO clearly shows improvement as expected over NSGA2. And this is significant, especially when converging to the maximum hypervolume, where NSGA2, as we saw previously, took about 17,000 observations, whereas we were able to converge to a given hypervolume in less than 500 steps, which is equivalent to tuning the accelerator in under 45 minutes. Now, on the plot on the right, if we look at the the current Pareto front after 200 and after 500 observations, we can see the two methods that the algorithm has at its disposal in order to increase the hypervolume. In the first case, in the I subplot, we see that we simply sample points in between other points in objective space in order to improve the hypervolume. And so in this case, this is improving the resolution of our Pareto front. The second case is simply just picking points that dominate previous observations, which is shown on the bottom right subplot. However, in this case, we found that more often than not, we are improving the resolution of our Pareto front as opposed to picking new points that dominate previous ones. And that's owed to the relatively simple nature of the objective functions in this case, which don't have many local extrema. And so generally speaking, when our surrogate model picks points that it thinks are ideal, they actually are ideal at the end of the day. Now, we like to add some specific cases in accelerators that we would like to modify this algorithm to be able to tackle. One of them is adding objective preferences. So in this case, I simply restrict my objective space inside of a certain to a minimum reference point and a maximum reference point, as shown on the left, and simply set the improvement to my hypervolume equal to 0 if a point lies outside of that unshaded, inside of the shaded region. And so an example of this is, let's say that we want to do our accelerator optimization, and we'd only like to, we have some preference that we would like the energy spread, for example, to be lower than a certain value. And so by specifying a new reference point, we can essentially cause the algorithm to sample more densely where it satisfies this preference. And that's what's shown here on the bottom. So on the top, I show the Pareto front after 500 observations in energy spread and transverse emittance objective space. And then I specify that my energy spread has to be less than some nominal value. And my algorithm only overall samples points that are below that objective, while still trying to find the Pareto front in that region of objective space. And since by adding this preference in here, I'm effectively reducing the objective space volume by a factor of 2, the Pareto front result is much higher resolution than in the control case, just because it spends more time searching in a very limited area. Now, another modification that we might like to make is we can say that we don't actually care, we don't actually are worried about minimizing and finding the Pareto optimal set for a given objective, but we just want that objective to be lower than a certain value. And so in this case, instead of constraining the objective space, we replace one of the Gaussian processes for the objective with another surrogate model that simply just predicts whether or not we have a high probability of either satisfying the constraint or not satisfying the constraint. And then we multiply our overall objective or acquisition function by this probability. And that's what's shown here on the right for our toy problem from earlier, where we simply state that we want we have a surrogate model for whether or not a point in input space is greater than or equal to 0.5. And if it's less, then we say that we satisfy the constraint. And if it's more, then we do not satisfy the constraint. And you can see on the right the probability map of whether or not our surrogate model predicts whether or not our constraint will be satisfied. Now, when we put this into Accelerator, in our Accelerator problem, we again specify that we want a certain, we don't want any solutions that are above a certain energy spread. In this case, by doing this, what we effectively do is we are relaxing the preference down to a constraint, which allows, since the optimizer is no longer trying to minimize energy spread below the certain value that we give it, it allows it to exploit the energy spread in order to improve the Pareto front in the rest of the objective space. So if we look at our comparison in energy spread and transverse emittance, we see that in the constraint case, a lot of our observations are showing up almost right at the border of where we are specifying our constraint. What this allows us to do is it allows the algorithm to improve the Pareto front in the other dimensions, for example, in transverse beam size versus transverse emittance, where we see that the green curve here, which represents the constrained Pareto front, is improved over the preference one. And obviously, when we reduce all constraints on our system, then we're able to find the best overall Pareto front.
Ryan, can I ask
Yes.
a question, please? So I'm a little bit confused. You are now showing sigma x as well. Is that also, are you optimizing 3 parameters, energy spread, emittance x, and sigma x, or you're just plotting sigma x to demonstrate that somehow there is a Pareto front appearing? So
right. So in this cases, we're still optimizing all 7 objectives at once.
Okay.
These are just projected into the subspaces of each of these 2 objectives.
Okay, and now we see, or you see, that the unconstrained, what do we see? The unconstrained Pareto front for emittance x and sigma x gets definitely much better if you constrain your energy spread. Is that
right? So essentially, it's the reason why we are able to find a better Pareto front in sigma x and emittance x is because we are allowing the energy spread to increase.
Right.
So it's always going to be a trade-off between those 3 objectives.
Mm-hmm. Okay.
And that's why the Pareto front in sigma x and emittance x looks worse when we constrain the increase in the energy spread.
Okay. Thanks.
Okay. And so finally, one of the things that is particularly important for practical use in accelerators is taking into account the cost associated with changing parameters inside of the accelerator. So in a computer, we can simply change a magnet strength very easily, and it instantly happens. However, when you are changing settings on the real accelerator, especially when there are very large jumps involved in the set points, it can take a significant amount of time to change that parameter and wait for the parameter, for example, to settle if we're using a current power supply or something like that. And then that also, in dealing with hysteresis effects, you also are wary of making large, frequent changes in set points, because that can start to introduce errors into the repeatability of your magnetic strength, field strengths. And so we want to basically come up with a modification to the multi-objective algorithm that takes into account these associated costs. So in this case, this is the control case. So this is my toy problem again. And what I've done on the right here is I plotted the trajectory of the points that I sampled in input space as a function of the number of observations. And what we see is that essentially in its attempt to maximize the hypervolume as much as possible, the normal algorithm jumps all over the place. And we can see that in the histogram of the distance traveled between each step, as a wide variety of distances traveled, including some very large jumps that we certainly want to avoid when we're using our accelerator. And okay, so the reason those large jumps persist is due to our acquisition function, which tells us where we're going to sample next based on our current surrogate model. So what we could simply do is restrict our acquisition function to only explore a very localized area around the last point that was observed. And that's shown here on the right. So you've got the red point in the center, which shows the previous observation. And we can simply restrict our acquisition function to be non-zero outside of the green circle shown. And that would certainly limit the travel distances that we travel in input space from step to step. However, one detrimental part of this is that it reduces the chance of us being able to take advantage of spaces that give us a really good value for our money. For example, if there are places that our surrogate model predicts that there's going to be a large increase in hypervolume, but it's just outside of this circle, we want to be able to exploit that area that is predicted to give us a large return on our investment. And so in this case, what I propose is that instead of doing a hard cutoff, we simply weight the acquisition function by a Gaussian distribution dependent on the cost associated with changing each parameter. So in this case, I simply specify a length scale associated with each input dimension. And that length scale is basically describes how expensive it is to change a given parameter. And then I multiply the Gaussian distribution centered at my most recent observation point by the acquisition function in order to make large jumps in input space more expensive. And we see the effect of that on the optimization of our toy problem here, where on the left, we have the unmodified acquisition function, which shows us bouncing around input space, kind of out of control. However, on the right side, I've specified a relatively small length scale that penalizes the large jumps in input space. And you can clearly see that the optimization algorithm slowly explores the input space, finding the Pareto front, and then traversing where we expect the Pareto optimal, where the surrogate model predicts is Pareto optimal, and jumping in much smaller steps than we did previously. Now, we need to be able to see if this works in the accelerator case, and it does. So on the top here, we see I've plotted the first solenoid strength as a function of the number of as a function of the observation number. And we see that during the normal multi-objective Bayesian optimization algorithm, this parameter jumps has very large jumps very frequently. And we also see that in the corresponding histogram. However, once we add this localized acquisition function term to our acquisition function, we significantly decrease the frequency and the size of large jumps in the parameter, excuse me. And then we can also compare how fast both of these methods increase the hypervolume. And we see that the smooth acquisition function, denoted as SUCB-HVI, we have very little cost associated with adding in this localization acquisition function term. So we are able to roughly optimize at the same speed as before, but with the improvement that we're not jumping around in 6-dimensional input space. So just to put everything together, so I've demonstrated how we take normal single objective optimization and adapted it to the multi-objective case. I've also shown how we can modify that acquisition function in order to solve problems such as adding constraints and dealing with taking into account costs of parameter changes. And these are all explicitly very relevant to final use in an online optimization algorithm. The results from our experiment or computational experiments are in this archive paper, which I can provide the link to anybody who needs it, and is recently submitted to PRAB. The next thing that I'd like to show, just to wrap up, is kind of the future direction that we're taking with this. So that includes efforts to improve the predictive accuracy of Gaussian process models, to expand the capabilities of the acquisition function, and to improve the optimization speed of the acquisition function for use in online optimization. So the first example here is towards the latter of what I just said, which is specifically optimizing the acquisition function in large parameter spaces. So we know in the Photoinjector case that we have here, we have maybe six knobs that we have, but in larger accelerators such as LCLS or the Swiss FEL, you have a much larger input parameter space, anywhere between 30 and 100 tuning knobs. And so what I've been experimenting with is using seeded swarm optimization to smoothly explore input parameter space in a disciplined manner in order to get over the curse of dimensionality. In this case, I've shown optimization of a simple test problem known as ZDT1. This test problem has 2 objectives in a 30-dimensional input space. And I was able to find the correct Pareto front in under 100 physical observations, which this problem is much closer to an accelerator problem due to the high dimensionality of the input space. The next thing that I'm also working on is taking into account time-dependent or drift and noise into the multi-objective framework. So as you see here on the left, our current framework uses discrete points to define where our Pareto front is, our currently measured Pareto front. However, if you take into account noise and potential drift, it might be the case that those points in input space are no longer Pareto optimal. And so in order to take this into account, instead of using a discrete point that defines our Pareto front, we have to define each point in input space as a probability distribution. And then in order to translate that into a hypervolume, which we then calculate the improvement of, we simply use a pessimistic viewpoint of where the current Pareto optimal front is, and then use that as our metric for calculating the hypervolume improvement for. This is an example of a modified toy problem with time dependence. So what I've essentially done is I've taken my two objective functions and I have them spin around each other. And the Pareto front in input space is shown here on the left by the orange line. And so we'd like points to be able, we'd like to be continuously sampling points on that Pareto optimal subset in input space. And as you can see in the animation, the most recent 25 observations in time, which are denoted by the red crosses, follow the little orange line around as the objectives vary in time. The graph on the right shows the log probability distribution from our surrogate model at each of the observed input points. And we can see here is that as the model evolves, taking into account the time dependence of each of the objectives, we are able to continuously make measurements that are on the current Pareto front. And so with that, I just like to conclude. So these are the things that we have been working on. These are the things that we will be working on. And hopefully soon we will be working on experimental demonstration of this in order to use it in accelerator facilities practically. And with that, thank you very much for your attention, and I'll be happy to take any questions.